Hi everybody, and welcome to MATH-segnale. Today we will talk about topology. When you think about topology, you will always have in mind the animation of a cup transforming into a donut. Today we will show you how this perspective impacts mathematics, telling you a really nice result about the intriguing world of Polyhedra. Take a look at this photo showing a radar dome. Its mathematical representation is a polyhedron with a lot of faces. Some of them are pentagons and the others are hexagons. Pentagons and hexagons. Where have I seen them before? Oh, in a soccer ball. So, what are the common properties? Faces are all pentagons or hexagons. Faces meet in group of 3 at each vertex, and both resembles a sphere.
Well, this not seems so precise. What do you mean?
You're right. Let's assume Polyhedra we are interested in are similar to a sphere in the same way that a cup is similar to a donut. You're ready for the intriguing result? The number of pentagons is always 12.
What? 12 pentagonal faces? Are you serious?
Absolutely. And believe it or not, this result follows naturally from a broader property shared by all Polyhedra that resemble spheres. Let's start from the beginning. Capturing our definition of Polyhedra can be quite tricky. Let's try to define what a polyhedron is. Done? Now, check if these examples fit your definition.
Oh, wow! These are some strange examples. So, according to the idea of polyhedron I have in mind, only the last two make sense as polyhedra.
Depending on the context, we can decide to include or exclude some of these examples. But today we won't delve too deep into this aspect. We assume we have a good definition fitting with the last two cases, guided by our intuition. If you want more information, we provide you some references in the description. Let's start with an easy polyhedron, for instance a cube. And let's count vertices, edges, and faces. In this case we have 8 vertices, 12 edges, and 6 faces. What if we do the same for a tetrahedron? These are the values, and do you see any pattern here?
Yes, I remember. It's the number of vertices minus the number of edges plus the number of faces is equal to 2.
Yes, and these are not specific cases. This expression holds true as long as the polyhedron is similar to a sphere. Let's take a polyhedron similar to a sphere and imagine inflating it and creating a strange planet whose regions are the original polyhedron faces. Our aim is to project our polyhedron on a plane, creating a map. Notice that it seems that one region is missing, but this region has been mapped into this infinite outside region.
I don't understand exactly your description. To me it seems easier to pretend the cube is like a room and we see the room from the top. So we remove the ceiling, we put the camera on the top, and this is what we see.
Yes, this is a great way to see it. Now, let's assume that all the faces are triangles. We can assume it since we can divide the graph into triangular faces. Since every time we add a diagonal, we are adding one edge and one face, and the value of the Euler expression is always the same. Now we want to remove triangles one after the other, maintaining the same value for the expression v minus e plus f. The goal is that in the end we will end up with just one triangle, and if we count vertices, edges and faces, we will have 3 vertices, 3 edges and 2 faces, since we have the outside infinite one. And since this value is maintained constant during the transformation, even for the starting polyhedron, we had the same value. But how can we remove triangles and maintain the same value? We have 2 safe moves. In the first case, you are removing a triangle who has 2 border edges. As you can see, in this case, you are removing 1 vertex, 2 edges, and 1 face. In the second case, you can remove a triangle which has just 1 border edge. Can you figure out why this is okay?
I get it. The second case is similar, because you remove 1 face and 1 edge, and so the result does not change. So we go on and on until we have just 1 triangle, and that's all.
Almost. Let's take a look at the 2 moves we mentioned before. You have to play your move very carefully, since if you do some moves in a strange way, you could end up with a situation like this one, where it could be tricky to decide which triangle you have to remove. In essence, you can decide to remove triangles with 2 edges on the border, or with just 1 edge on the border, but not all the 3 vertices. These are safe moves, and this will guarantee that you can end up with just 1 triangle without any problem. As we said before, with this graph we have that v minus e plus f equals 2. And so, we completed the proof. Now we are ready to prove our main result. Let's write down what we know about our polyhedron. Faces are only pentagons and hexagons. And for the vertices, every hexagon gives us 6 vertices and every pentagon 5 vertices. So we have just 6 times the number of hexagons plus 5 times the number of pentagons. No! Since every vertex belongs to 3 faces, you have to divide by 3. And as you can imagine, for what concerns the edges, we have 6 times the number of hexagons plus 5 times the number of pentagons divided by 2, since every edge belongs to 2 faces. If we put all these informations into the Euler's formula, the hexagons cancels out and the number of pentagons has to be exactly 12. Well, someone could say the dodecahedron has exactly 12 pentagons, and we already knew it. The soccer ball has 12 pentagons and 20 hexagons. Ma davvero ha 20 esagoni la palla da calcio? Figo. So, what's new? This theorem is saying that if you try to construct a polyhedron with hexagon and pentagons meeting 3 at the time at each vertex, you have to use exactly 12 pentagons. We think that the result is really wonderful, since this property seems to arise for some magical fact, just using a property and not looking at a specific example. But there is a catch. How can we prove that a polyhedron with these characteristics exists? Well, we know that there are some examples. For instance, these. So now the next question is, how can we guarantee the existence of this polyhedron for every number of hexagons? Maybe there are just these 2 cases, so with 0 hexagons or 20 hexagons and no more. The correct statement is that this kind of polyhedron exists for every number of hexagons except 1. Now let's start with the proof. For n equals 0, we have the dodecahedron, so we are done. And since in the statement we say that for n equals to 1 is impossible, we start with n greater than 1. And in order to do this, the idea is to construct a graph similar to the graph we used for proving the Euler's formula. And we will do like in a puzzle game. we have just 4 pieces and 2 starting frames. Every time we put a piece into the starting frame, we are adding a certain number of pentagon and hexagon. Now, let's try to construct some examples.
Okay, so if I want 2 hexagons, I use this frame and this piece. If I want 3 hexagons, I use the same frame and this other. And so for 4 hexagons and 5. And if I want 6, I use this plus this. And if I want 7, I'll do like this. But wait, how can I obtain more hexagons? You said any number was allowed.
If you want more hexagons, you have to add 1 special piece. In this case, you have 6 hexagons and a little space in the middle, so you can use it like a frame, since you can put inside one, the original 4 pieces, or another of these special pieces.
Okay, I got it. So for instance, if I want 9 hexagon, I can use 1 special frame, like this. And for instance, if I want 14 hexagons, I can use 2 special frames, and I got a drawing like this. Nice! How can you find a polyhedron with 12 pentagons and just 1 hexagon?
Why do you want to do this? Our theorem was about all polyhedron with a number of hexagons different from 1. But if you want to prove that it's impossible to obtain the polyhedron with n equals 1, you can try to do it by yourself. Here is a hint. So, now we are left to prove the existence of the polyhedron itself.
Wait a second, isn't this what we just did?
Not exactly. Since up to now we have constructed the graph of the polyhedron on the sphere. But we want the old good polyhedron with the flat faces. And as you can notice, for instance, these 5 points may not lie on the same plane. The easiest way to prove this is use a powerful tool known as Steinitz theorem, which asserts that if we have the graph on how the edges, faces, and vertex of the polyhedron connects each other, and there are some properties true in this case, then there exists a polyhedron with this graph.
Okay, but I was wondering, is there a way to visualize this result without invoking such a powerful theorem?
Yes, if we don't want to use Steinitz theorem, we can visualize something using a kind of duality concept. Consider the diagram we want to realize and take the center of the faces. You have to connect the center of nearby faces, obtaining a new diagram called the dual diagram. As you can notice, now you have only triangles, since in the original diagram every vertex has 3 nearby faces. Now you have exactly 12 vertices with 5 nearby faces, and these 12 vertices were the center of the 12 original pentagons, and the same holds for the hexagons, which now are represented by a vertex with 6 nearby faces. Go back in the 3D world, for instance via stereographic projection, trace the edges, and now we have our polyhedron with triangular faces. And why this is important? Well, since triangles are always flat. This is not our original polyhedron. We want the polyhedron with pentagons and hexagons, not with triangles. And we have to do a duality-like construction, but in the 3D world. A possibility to do this is to draw the radius for every vertex and then the tangent plane. If you do this construction for every vertex of your polyhedron and you intersect all the tangent planes, you will end up with a new polyhedron. In our case, every vertex with 5 nearby faces will generate a pentagonal face, and in the same way, every vertex with 6 nearby faces now will generate an hexagonal face, and so we have constructed exactly the polyhedron we were aiming for.
There is so much magic in this result. These are the two things we like the most. First is how explicit the power of topology is, because this does not work only for polyhedron, but for whole polyhedra-like shape you can draw on a sphere. Try it. Take a balloon and try to draw some lines on it to resemble a polyhedra which follows our rules. The only possibility you have to complete the drawing is if there are exactly 12 pentagons.
And second, we love how we played with mathematics during the video. For instance, are you wondering what happens if you use another shape instead of pentagons? Are you wondering what happens if you want to use pentagons but on a donut-shaped polyhedron? Let's give it a try. Most of the time, playing with mathematics is doing mathematics. Playing with formulas, numbers, objects, manipulate them in order to get a new theorem. It's like a wizard playing with words in order to get a new incantation. So let us know in the comment, when was the last time you played with mathematics? That's all for today from Davide, Riccardo and MATH-segnale. Bye!